Hi everyone, we are back and now we're going to get into linear fits. So often, again, we're going to be working with data files, extracting data files, and we're going to be looking and trying to fit and analyze our data. So what I'm doing here is, again, taking our bending and I'm just looking at all of our bending data. So all dat. So we can kind of see right here. So again, here we're seeing all of our data. So again, it's all the multiple files, and we're looking at, again, we want to plot the displacement here versus the force here, I believe. So we can go ahead and look at that here. And this is all of our, again, our nice bending data. So let's go ahead and let's pull out one of the data sets. So this is our first data file here. So looks pretty nice, looks somewhat clean. So let's just go ahead and let's try to fit this entire data set. And when we do that, so again, how does this function work? We're looking at list line plot. So what this is saying is, we can kind of piece this out one by one. We can go ahead and see here. So looking at this, we're fitting the entire data set. So this XY. So when we show the plot, as you might anticipate, it's not a great plot. And actually we can kind of make this, let's do plot style. Let's do red. So not a great fit. But we could go ahead and narrow down the range. So for example, I could see here that, let's go ahead and search between, let's start at 1, and then let's go all the way to, let's do 1 to 3. That looks like a pretty linear range. So I want to go the nearest to 1, and I'm looking here, see, I'm grabbing all of my first column, so my displacement. So I want all of 1, I'm going to find this. So that's the value, and then I'm going to take this, I'm going to copy it in here, and then the nearest here. So that's going to give me that position. And I could do the same bit of code to find for, what do we say, like 3.3? The nearest to 3.3. So 61. So I can take from 201 to 661, and I can narrow down that range. So what I'm doing here is taking only a subset of my data from 106 in terms of my millimeter displacement to there. Now I can go ahead and plot this and see how it looks like. Much nicer. Very, 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 very good here. Let's say, for example, instead of narrowing this range, let's say we went from 1, you could see then that our plot's going to change a little bit. So we could see that that value changes. So that 201 gives me a nice fit. We could also fit another way. So you could take the same bounds here, and you could do, instead of fit, you could do find fit, and then actually give it a functional form as well, and ask for your fitting parameters, and you can get those values here. You could do also a linear fit model for those, again, same bounds, and then you could grab that data. There you go. So this is very useful. This linear model fit is a great one. You can't, for example, I can't do like now for, I can't do a plot of LM from X from, 0 to 10, for example. I can't do that. But if I do normal, then it allows me to kind of basically look at this function. So then you could fit it and plot it. What happens when you are working with nonlinear functions? So luckily in Mathematica, again, we're very fortunate, we have the ability to basically look at that nonlinear model fit. So let's go ahead and let's go from 1 to, let's go from 1 to -1. So I could do this. I could see my, again, I'm looking at this kind of exponential type of curve here, and let's see how it looks like when we plot it. All right, so see, it's cut off. We don't want to go from all the way to 1. It's a pretty nice little fit, actually. But let's go ahead and let's cut off like the first couple points and the first, couple points here, because sometimes the zeros really kind of mess it up. So let's fit it here. And actually, instead of, let's do 0.01. Let's do our plot. Anyways, we've lost some values, but actually we've got some nice little functions here. So that's very, very, very good. Yeah, that's a really, really cool fit. I'm sorry, I'm just admiring my own. We can also look at it as a log function as well. So, for example, we can go ahead, actually we could look at plot range, sorry. I want to just do a little bit. And actually what we could do, there we go. So you can actually see it right here. So that's a nice, that is a pretty good fit. So this exponential curve. Now is it physical? No, so don't worry about it. Here, we can go ahead and look at here, and then let's go ahead and try to plot this as well. Let's do plot range wrong. Again, not a bad function for, log and, kind of fitting here. So the key thing, again, we want this to be physical. So we could improve the fits quite easily by adding in 10 or 15 different fitting parameters and functions, but we need it to make sense kind of logistically and physically. Oftentimes it may be beneficial to plot on a log-log plot. So for example, I could do a list log-log plot, as you can see here. So log axis on the Y, log axis here. So you can kind of see those values. I could do list log-log line plot, or actually this log-log plot. Actually, do we have line list or list line? No, because again, why don't we have line? Because it's actually really messed that up. So we can see our values here. We could do a log scale, a list log plot. So you can see we have the log on the Y, and then X is kind of your normal function. Or you could have a log on the X, and then just a linear scale on the Y. So lots of different kind of abilities to plot. These are very beneficial in certain circumstances. A log-log plot can make a lot of physical sense. So next time we're going to jump into some statistical measures. So we're going to look at some Gaussian, some central limit theorem, z-score, t-score, and then some ANOVA analysis. And then after that, we'll kind of see how you can get some statistics based on your plot. And then, yeah, after that, we'll be pretty much done. All right, I'll see you in the next video. Thanks. Bye.